Chapter. I know my wait let me cut this one. Then I can have a better control. Okay. I want to put it at the side here so that we can see easily. Okay. Now, this is the answer given by Brian. Brian really hardworking. Okay. Before, of course, okay, we look at these questions here. Okay, we need to understand these programs. These programs here actually is trying to get you all to familiar with the structural model. All right. And of course, okay, I can't be giving you all a very complex structural model here. So because, okay, otherwise, okay, we have to generate a lot of components first. Then only I can start doing this part here. So I assume that, okay, I have written some programs already stored into the database already. And now I want to reuse it. Okay, how to reuse it? Okay, in this structural model. So you find that I'm going to write a top level lah. We call it as a top level. It's something like saying that, okay, you have one. Wait, what's wrong? Okay, can I write here? Okay, I erase later. I have a top level. Inside this top level, there are many different components. Okay, different components or different entity. So I make use or I call this entity out and to be used here. So this program here is actually this one. Okay, it's actually this one. Those components here are actually the sub of it, or components which you are going to reuse or recycle. Okay, so we are writing this one now. Okay, this one now, the top level, so-called the top level. In your assignment, you find that, okay, I have one called top level. This is the one that I'm referring to. Okay, so my list top level here got 4 inputs, 1 output. All right, very simple design. Okay, then how does it look like in this top level here in terms of structural model? You find that they use 1 component, 2 component, 3 component, 4 components. And these are components here, I may use it more than 1 time. Okay, same components, I may use it more than 1 time. So I call out whatever components that I want first. And when I call out this component that time, I call out the interfacing parts. Their input pin and their output pin. This is what we call the interface part or interfacing part. Inside how you work, I don't care. Okay, I don't care. I only want your interfacing. So each one we call out. Okay, then to join this component together, we need to have some wire. This wire here is labeled as signal. Okay, labeled as signal in VHDL. And to make us, okay, understand better, okay, we may thought of using, okay, something that we see, then we can really figure out, okay, know what does it mean. Not just wire, WXYZ, things like that, okay, but with some meaning. All right, so therefore you find that you have a signal A bar, B bar, C bar, W1, 2, 3, 4, and so on. All right, okay, so you have component already, you have a signal already. That means that all the raw materials are ready. And now, how to connect them? This part tells you how to connect them together. Okay, so first one here says that I'm using not 1, this component is a not one. Actually, it's a not gate. But I cannot use not lah. Why? Not is a reserved word. Have a special meaning one. Okay? Therefore, label it as not one. I use this component. Not one. I do the port mapping. Port mapping means that the interface part. So interface in this case here, refer to here. First location, second location. Okay? First location, second location. So in this case here, sometimes the name may not be exactly the same. So, but in this one here, exactly the same. So this part here refer to the input. This part refer to the output. Here tells you that this A. All right. This one here is my A bar. And this A bar is a wire. They tell me these connections of not one is connected to the input A and their output connected to a wire called A bar. Then I use another NOT gate input connected to a B. This is input. Now you connect it to B. Location, first location is input. Okay, so input I connected to B. Their output I connect to B bar. Okay, I make it simple, put it this way. So this is my B bar. So the output I connect to a wire called B bar. One more, C location. Okay, first location actually referring to input. All right, their output I connect, okay, to a wire called C bar. Okay to all for this part here. Okay to all for this part. So now we are doing, okay, map it with location. You can do it this way to make it, okay, your programs here more simple. Of course, okay, you can also do exactly the same like what is on top there. I mean in our notes here, put it as you can put this one here as the C connections. I always forget, okay, which one should come first because I always use this method. Okay, you can also put it as, okay, your C. Okay, C is connected to your okay, this is the signal output. So first location. Okay, C is connected to your first location is your A. It's a bit confusing. Better don't do it that way. Okay. So I repeat here, we go by mapping of location. First location, input. Okay. So when you put your C here, that means, okay, your list input, I am going to label it as C. All right. Second location is the output. So if you put C bar, then you say the output, you label it as C bar. If you put B bar, the output, you label it as B bar. First one, you may say that exactly the same. Yeah, you can do this, no problem. Okay, this is the A bar. So I have done for this one. Then next, I need to know is because this is a not gate. So like I say, okay, your mother may have 3 children, so you want to name all your children, so you cannot have everyone call not one. So what we are going to do here is I am going to label this one here as N1. Okay, this is what we call instantial. N1, this one here, we name it as N2. This is the N3. Okay, next we proceed. And now we already have this one ready. Then now, okay, I'm going to use the N2. N2 is here. Okay, first 2 pin are the input, Z is the output. And based on, okay, this in mind, your N2, you are going to connect it to first input connect to A bar, second input connect to C bar. So connect to A bar, connect to C bar, and you name this one here as A1. A1, A1. Okay? And their output, you are going to connect it to a wire called W1. W1 wire. So this is a wire. Maybe I put something like this. Wire. Okay? W1. So done for this part. Next. X NOR 2. Okay? First two input, that is the output. Connect to BD. Okay? B, all right, and D. So D in this case here, I would prefer it to be drawn in the input so we can see clearly as an input. Okay, so okay, so this is the D connected to a D. Of course, nothing wrong. All right, put it this way, nothing wrong. But it would be good, okay, to label A, B, C, D. All these are input. So this is my X. Okay, X NOR 2. You are going to name this X NOR 2 here as a NX1. All right, NX1. And the output here, you connect it to W2. BD are the input. W2 is the output. One more, N2. So you use N2 two times, but you only call one time. You use NOR gate 3 times, but you also call one time only. All right. And this N2, I'm going to connect to B bar, which is a wire, C input, W3. Okay. B bar, C, W3 is a wire. All right. WR wire. Okay. Done. And you label this one here as A2 to differentiate it with this one. All right. This is A1. This is A2. So next, okay, A3 again is an AND gate. W1, W2, W4. W1, W2, W4. All these are wire. All right. And next, the O1. O1, okay, is connected to W1. Input, output are W3, W4, W3, W4. Well, in this case here, with the bullet, is it okay? Because first input, second input, this is output Z. First input, second input, Z. No problems for all gate. Okay. If it's other component, maybe a little bit confusing. Okay, may cause problem. But for no gate, for gate, simple gate should be no problems. Okay. So you arrange it this way, and this one here, you label it as O1. And actually, okay, all these are inside your a component. Okay. Your interfacing part is this one, ABCD. This one, don't kacau. Okay, ABCD. Ryan, your drawing is better than my one, no? Very good drawing. Okay, so your ABCD are the input, Z is the output. And of course, here I list out this one here is for you to confirm your answer is it correct. Okay, double check. Is this answer correct? So this is the A bar. This part here. A bar, we write in terms of this logic. So this is A bar. A bar, this is the C bar. A bar, C bar. This one here, X NOR gate. Okay. B, D. Okay. X NOR. If I use symbol, how does it look like? NOR gate. NOR gate. The symbol, if it's correct symbol, this is a NOR gate. X NOR gate should have one more here. Means that this one here should look something like this. Okay. Now, if this is the B, this is the D. Okay. X no is okay. We start off with this. This is a X O. Remember this? This is a X O. If you put a bar across it, it then becomes X no. All right. So this is the X no expressions, which is the same as this one. I remember why I typed in this one already, because I couldn't find this symbol, these are things, okay? So that's why I just type it as X no. All right, so this one going to here, therefore you end it, you are going to get these expressions, whole thing. And after that, this is the OR gate. What I need to know is a W3, okay? This is a B bar C. Okay, so confirm that this expressions here is correct. Okay, good. Anyone wanted to ask anything? Class, are you all with me? Brian, you are doing a good thing already. Very good. Okay, any questions? Anyone with any question? There is our tutorial number 2. Okay, now do you all want to proceed with the third tutorial? Writing programs already. Do you want to proceed, or you need more time to familiar? So in this case here, shall we proceed with lecture? Okay, I also should ask, next Monday, next Monday, right? Where are we supposed to meet? Virtually or in the campus? Next Monday, because next Monday is week 5 already, okay? No, we talk about lecture first. Monday, no lab. So next Monday, am I going to see you all virtually or in the class physically? Adin virtual. Brian, okay, you follow majority. I think virtual better for now, because of Omicron. More than 10,000 already. Okay, so next Monday still virtual lah. Because I need to know, you cannot suddenly say you want to see me. I need to go to campus one. Okay, so next Monday still virtual, except lab. Am I right to say? Is still okay? Week 5. Week 5. Only lab is face to face. Okay, and lab is on Thursday, not mistaken. Very blur already. After need bring lab coat. What lab coat are you going to bring? No need. Okay, no need. This is not doing chemistry lab. No need. No need. Okay, just bring yourself, bring your programs. Okay, bring yourself, bring your program. In bachelor, no need. Okay, so bring yourself, bring your program. If you want to bring your PC alone, of course, no problems. Laptop, no problems. Do you all know where is Q200? Lab is in Q200. Very far away, very remote, okay. Well, okay, maybe I go and search for the college, okay, the plan, then only I talk to you. Now don't waste the time, okay. So I will see you again on Thursday, isn't it? Okay, so I find the plan, I tell you all, quite far away from the main entrance. And our class is 8 o'clock in the morning. All right. So I'm not sure, okay, for your, will they allow you to drive in your car if you're coming with a car, because you got no sticker, this and that. Usually to enter campus, okay, you need a sticker, isn't it? But now I don't think, okay, any one of you having the sticker. So and you can't park the car near to the lab, okay, because that one is reserved for staff. Okay, so I will tell you, I find a fall plan first, okay, and tell you on Thursday when I see you again during the lab, as well as another 1 hour of lecture. Okay, so Monday, next week, Monday, lecture. So if really that bad, the lab also actually we think about it. I know everybody is worried. Okay, I also worried because I'm older than you, much older than you. Okay, so we can talk about it, okay, again. Okay, so tentatively only Thursday lab is for this physical next week. Okay, so any more question related? Okay, if not, I think I'm going to stop my lecture and I'm going to record. Okay, no questions, Okay, let me wait. Check whether my this one is it ready. All right. Okay. Let me record first. Okay, can you all see my screen here? Can you all see my screen here? Okay, good. So now you are going to find that, okay, when we are writing VHDL programs, okay, very frequent that we may just write whatever logic that we want the VHDL to perform. For example, just tell them, this one, when this condition, S is this condition, you force the max output to take the C input. When S is a different condition, you take, okay, max output as the D input, things like that. Okay, we just go by sequence. But in reality, okay, this go by sequence here, okay, requires some time, okay, to process. So there are some, okay, delay in actually producing the answer for you. But because nowadays the hardware, okay, is working so fast, okay, in maybe picosecond, nanosecond. So you didn't realize that actually, okay, there is a little bit of lack of time, okay, when you are supposed to obtain your correct answer. But for some designer, okay, whereby they are going to produce a very high speed, okay, hardware, then they might need to take care of some delay, make sure that the timing they receive the information is proper, things like that. So because of this, okay, so we look at a little bit of this delay model in VHDL. So you're going to find that there are 3 different types of delay model. We call it as inertial delay, transport delay, delta delay. Delta means it's a very short time. Okay, very short times. Okay, look at inertial delay first. It's a default delay model, suitable for modeling delay through devices with inertia such as gates. So if you were to look at the how I say the data sheets of any of the gates, okay? They will tell you this gate, for example, require 10 nanoseconds. Just take some simple figure, 10 nanoseconds to respond. So let's say, okay, I have inputs here, A and B. To get my output Z here, for example. So this one, okay, I input, okay, or data, the input data is right here at time 0. I can only get the correct output Z. Okay, correct output Z after, okay, after 10 nanosecond later, you get your correct output Z. All right, so this is what is being meant by inertial delay. My gate requires some time to respond. Actually, what is inside the gate? I hope you all still remember what you studied under basic electronics. Inside the gate here, actually, you have transistor lah. All right, you have transistor, you have a diode, of course, a resistor. Okay, these are the basic components inside this gate here. Transistor requires some time to function, react. All right, so the reaction time in this example here, I take it as 10 nanosecond. So for example, now, okay, your this set, let's call it as Z1 here. This set output, okay, forms, okay, the input of another AND gate, which come from the C input. So to get the correct output now, you find that you need 20 nanoseconds later, because correct answer for this one is 10 nanosecond. If this one no delay, starting is already there, but they may give you the wrong answer. Okay, if this output here is changing from, say, for example, from this 1, then change to 0. You find out, my answer, how come suddenly change, okay, at the time 20 nanosecond? This is because reactions proper signal from Z1 arrive already. Okay, so this is the inertial delay. So that to say, okay, when you are writing any VHDL program, if you want it to be very exact, okay, you have to incorporate all this delay into your programs. All right. Okay, next. Second one is a transport delay. Model delays through devices with no inertial wire. No, wire actually can transmit signal very fast. Of course, okay, faster than this 10 nanosecond here. Maybe it's just 1, 2. Okay, so no inertia. There are no inertia. All the input events are propagated to output signal. So we are going to take as a wire here that is having, okay, very short delay timing. And this delay timing here, we are going to call them as transport delay. All right, transporting. So of course, okay, shorter wire is better. Your transport delay will be shorter. Okay, will be shorter. So you can get your answer here faster. Okay, so this one here maybe is 0.001 nanosecond, very short wire. Okay, so although very short wire, but we also must know that there is actually a transport delay here. Remind us that when we are doing designing, okay, we try to design, okay, wire, a shorter wire. All right, next is the delta delay. Okay, so in some of these design here, you are going to find that, okay, we never put down the how much is the delay time. We never specify. Okay, and this delay, okay, will be propagate. Like I mentioned just now, this is 10, this is another 10. We assume both of them are having the same inertial delay. Then propagation delay to get this actual output here will be 20. All right. So what happens? Okay, I didn't know what is this. I didn't know what is how much is this delay, and this how much is this delay here. You are going to find that actually system itself, okay, is going to incorporate some short delay for you, which they label it as delta delay. Okay, you never put, but system needs time to respond also. So they add in the delta delay. And this delta delay here is a very short delay lah. So nanosecond. Okay, now they will insert, okay, several, okay, nanosecond, okay, by the simulator to preserve the correct ordering of the event. Smart enough, okay, to do all this lah. All right, okay, we look at this further example on this inertial delay. Now, let's say I have an input. This is my input signal that I put in for this OR gate. This OR gate here, two different types of OR gate. First OR gate here, the delay here is 10, okay? Out what now? Out here, output here, gate propagation delay is for this case here, yeah, sorry, it's 8 nanosecond. That is to say, to get the output correctly, it must be 8 nanoseconds later after receiving the input. In this example here, one input is directly shorted to ground, so it's for level 0, no problems. So it's this one, okay, that decide when am I going to get the correct output. All right, so first, this is the input and this one here is 8 nanosecond. Okay, look at this input here, timing. This is 5. Every segment here is 5. Okay, so this one here, duration is only 5. This one here, duration is 10. All right, and this initial delay for this OR gate is 8 nanosecond. So if this is the case here, at the output here, you are going to find that with this initial delay of 8 nanosecond, they will reject any of the input signal less than 8 nanosecond. So at the output, you only see this one delay by 8 nanosecond. So this signal habis already, gone already, no more. So when you have when you are written this one here as a out1 inertial input after 8 nanoseconds here, means that you are rejecting any signal less than 8 nanoseconds. Okay? Because you consider you don't want the output here, no, unstable, this and that. So you reject whatever signal less than 8 nanosecond, okay, to be output to here. So you find that this one here, 5 nanosecond here, has been rejected. You don't see it. But this one, yes, I delay for 8 nanosecond and same pattern, I'm going to see it. Okay, this is the output 1 with 8 nanosecond. If now, okay, you take this higher performance OR gate with 2 nanosecond, okay, 2 nanosecond, you find that no problems. This is 5 ma. So I delay for 2 nanosecond. I can see the pulse here. And this one also delay faster. So this out2 having higher performance as compared to out1. All right. So you find that, okay, out2 can be written here as input after 2 nanosecond. So this is normally what we are trying to do. Or you can insert the inertial delay here as inertial input after the 2 nanosecond, which indirectly you are rejecting any signal less than 2 nanosecond to be shown at the output here, so that your output is stable. Okay? Because in the hardware also the same thing. Any signal sometimes too small, they will just, they cannot detect it. Signal is not there to be sort of read. So imagine, okay, if we people, human being, somebody pass by us very fast, okay, too fast for our eye here to respond, I'm also going to say that I cannot recognize, even though I know him. I'm not sure whether is it this person or not, because signal is passing too fast. So in this case here, if the signal is faster than the inertial delay of the gate, they just don't respond. Okay, just like our eye here, don't respond. Couldn't see, don't know who is that person. All right, so remain no signal being detected at the output. Okay, so this is the inertial delay, but all the timing here will be in terms of nanosecond, this type of part. Okay, next we look at the transport delay. Okay, transporting of a signal. So look at this part here. We have a signal. Transporting delay is related to signal, the wire. Okay, so we only focus on the architecture. My architecture here is a half adder. It's something to do with a half adder. Two signal, S1, S2. Okay, when you see this, it means that both S1 and S2 start from 0. This one here indicate to you initial value. I start from 0. S1, S2 both start from 0 because you define already. Some students may ask, if I don't define how? By default, actually, is also 0. But you define will be very clear that it is a 0. Okay, how I want my S1 and S2 here to function. I want S1, okay, to be assigned as A X naught B after 2 nanoseconds. And for S2, I want A end with B after 2 nanoseconds. After all this, okay, I transport S1, okay, transport S1 to actually sum lah after 4 nanoseconds. And transport S2, okay, to the carry after 4 nanoseconds. So with this, okay, we'll see how it is being shown here. So these are my AB, sum, carry, S1, S2. This is the time, okay, time base here. Every segment, 2 nanoseconds. Okay, because here are all the multiple of 2. So 2 nanoseconds. Start off with, okay, 0. As I mentioned, this is a 0, this is a 0, initial value. What is the output here for the sum? What is the output here for the carry? Don't know, not sure. Don't know, not sure. So you find that, okay, a lot of these are signal hatching. So if you see in the simulations of your VHDR, you also see, okay, signal. If you ask me whether they are logic 1 or logic 0, I'm going to tell you I don't know. Okay? So uncertain signal. All right. Okay, my A and B input start off with, okay, my A is at logic 1 for 2 nanosecond, B logic 0. And A keep on changing. After every 2 nanosecond keep on changing. B pattern varies a bit. Okay, based on this programs here says that A XOR B. Still remember XOR, sorry, okay? A XOR B means it's A bar B plus A B bar. This is XOR expressions. Okay? XOR expression. So that will say A and B cannot be the same lah. Okay? You see A bar B, then A B bar. A and B, as long as A not the same as B, okay? S1 is a 1. Okay, as long as they are not the same, S1 is a 1. This is how I interpret these expressions here. Okay, so I do this. So I find that my S1, I use this one, XOR first. Not the same, this one, not the same for 2 nanoseconds. And show this result after 2 nanoseconds in S1. So you find that whatever combinations here will be shown here. This one is shown here. This part N here is shown here. So delay of 2 nanoseconds. Okay, delay of 2 nanoseconds. Then subsequently they are the same, right? They are the same, right? So therefore 0. Only when they are not the same is a 1. So they are the same, right? 0. So this part, after here, you find that they end here. But here they are the same again. Okay, they are the same again. So you see another 0. Then this part here, this is 0, this is 0, same again. Okay, you see that is a 0. Come to this point, come to this point. This is 1, this is 0. So not the same. So I give you a 1 for my S1. And for all this S1 here, you only get the result after 2 nanoseconds. Okay, the correct result after 2 nanoseconds. So there's a delay of 2 nanoseconds. Okay, that is the first one. Okay, S2. S2 is A and with B after 2 nanoseconds. And in this case here means that they must be both 1. Then my output is a 1. Okay, both 1 output will be a 1. Okay, so where am I going to get my both 1 here? So we mark first. This is the 1. Other than this, okay, here. All right. Here, I may be getting a 1 at the output here after 2 nanoseconds. So you find that I get this 1 after 2 nanoseconds. This one not shown already because N here. Other than this, okay, they are not the same. Okay, so you find that, sorry, both of them, okay, are not at the 1 condition. Therefore, you find that the S2 are forever 0 in 2 nanoseconds. Okay, the delay happens over here. This one you cater for it, okay, you plan for it. Okay, transport delay. So they need 2 nanoseconds to do the perform it, and then tell you the results. Okay, delta delay is something that is a very, very small time delay. Maybe is smaller than your nanosecond, could be is in terms of picosecond, things like that. So look at a simple example of this one here. Okay, so I got 2 inputs, 1 output. Inside here are all the wire. All these S here are all the wire. So S1, not yet of in 1. S2, not output of into. Okay. S3, you not because of this one. Okay. Then you take S1 and we into purposely want to make it a little bit complex lah. So you end first, then you not it. So this part here is a function exactly the same as NAND. Okay. S1 NAND with into. This one is the S2 NAND with in 1. And this one S3 NAND with S4. Okay, so very simple process. And with this, okay, how we are going to sort of understand the delay timing. You see over here, we never specify, okay, my S1, I will get the result after how much time. Okay, after how much nanosecond or picosecond for each and every one here not being specified. Okay, but the simulator itself will specify it or will allocate the timing for you. So when they allocate the timing for you on their own, we say that, okay, delta delay timing. The simulator itself, okay, allocate some time for them to react. Okay, so I'll enlarge a little bit because very small. Okay, now this is my input 1, input 2. Okay, this segment, the H1, okay, has been enlarged to be shown here. Okay, it's being shown here. This part, hatching one, okay, has been enlarged to shown here. So we will look at here as in 1, no change. Okay, unchanged signal. So in 2 is the 1, got some changes. So whatever, okay, changes, okay, in 2, in this case here, if you were to look at the programs here, it will affect your S2. It will affect your S3. Of course, okay, once it affected this S3, it will cause your Z here, okay, also being affected. Sorry, S4 also, this is S2. I see the wrong one. Okay, into affect S2, S2, affect S4. Yeah, okay, so it's a 2, 4, and the Z, okay, will be affected. Okay, two. Oh, into. My eye really, correct, into, not in one, sorry, okay, 2, 3, Z. Yeah, 2, 3, Z. Okay, so these are the signal will be affected due to the changes in the into. Okay, so my these are then to change the time, my X2. S2 in this case here, it is given by the expressions of, I cannot see, okay, on top. Now into, okay, S2, okay, is given by the expressions of not into. So I make it simple. It's a not into. So you find that, okay, they will automatically when here change. These are S2, okay, the balik not okay, change. But how much time they need to change? See at the bottom here is this one is called delta time. Delta time is a infinite, okay, infinitesimal time means that is a very, very short duration, less than maybe 1 nanosecond. All right, so it take, okay, 1 delta time to response for this S2. And for the case of S3, because, okay, it is S1, okay, NAND width S1 NAND width, okay, this is a NAND, and really then you bar it become NAND. So it's given as, okay, S1 NAND width into. So when into change, you find that, okay, my S3, okay, will also react because of only one variable. Only one variable. So you find that they react, okay, due to these changes here also with 1 delta time. Okay, 1 delta time. Seems like they react exactly the same. This is the by drawing. In reality, in the hardware may not be the same because different components may have different reaction time. Okay, then subsequently the Z is given by S3, S4, you name them. Okay, so I need to have a stable S3 first for this case. All right, then, okay, I end it with S4 and I not it or NAND with S4. So it requires another delta time. So you find that for your S2, okay, to get a correct output or stable output, you require 2 delta time. So of course, this delta, it could be, I repeat here, 1 picosecond, okay, or 2 picosecond, things like that. May not be exactly the same for all hardware components. But here is trying to tell you simulator itself. When you, okay, make the timing very small, you actually find that, okay, they need some time to react. It's not exactly, okay, at the same time. Okay, not exactly at the same time. A little bit of delay changes. So therefore, okay, when you are doing any simulation that time, don't ever, okay, if this is the input, don't ever try to see your output exactly at the same time where this is changing. Always, okay, take a little bit of delay. Okay, I want to see the output, okay, at different timing. Okay, and if you have two signal, okay, where you want them to perform, don't always, okay, make the changes happen at the same time, because your list same time here is maybe, okay, a changes of 1 delta time, then your output you may see a spike comes out. Then why this happens? Answer is because overlap of signal. All right, so should I consider this one? Oh, in terms of hardware, actually they ignore it. They ignore it because too short, the duration, the signal is not stable. All right, So here it's trying to tell you, although you never specify any timing, okay, but simulator, when they want to do simulation that time, they themselves will incorporate, okay, a short durations such that, okay, they can produce the correct output for you. Okay, so in summary, this one here for devices using gates. Now, when you say these are inertial delay is for gates, don't forget, okay, all your components, say for example, multiplexer, decoder, encoder, even though your flip-flops, all are built up using gates. So initial in this case here means that the device that you are using, all devices that you are using here require some time to react. So the time required, okay, for reacting is referred to as inertial time. All right. So you must make sure that, okay, this inertial timing here is shorter than the pulse that you want to transmit. Otherwise, they will reject the signal such that your output will become incorrect. Okay, next, transport, more for your wires. Okay, more for your wires. You model the elements such as the wire. Timing also shorter. All right, so you are going to find that if there are delay, okay, so the delay will be propagated. Depends on how many devices that you are using. Every device, okay, if they have the same timing, okay, so you go through 5 devices, then you are supposed to times 5. If not, okay, different timing here, you sum each and every one that forms the delay timing for that particular entity, okay? Next, delta time, automatically. You never write, programmer never write, system insert for you, okay? So to ensure functional correctness of the code that do not specify timing, you never specify, they add in so that it work properly, okay? So especially in the data dependency on the code. Okay, so I need the signal coming in from previous, okay, entity or previous gate. So I need the timings here. So this is the delay model that we are talking about. Okay. Now we take a break, digest. If there's any question, because later on here is on latch and flip-flops already, slightly different a bit. Okay, any question that you all want to ask? No question. Okay, then 5 minutes break. Is it okay? Okay, see you all again at, we will continue until 1 o'clock today. We bring forward our lecture. So 12, 1, 2. Stretch your body a bit. I already sit here for 2 hours already. Okay, class, shall we proceed? Any question? If no, I continue. Okay, recording start. Okay, can see my screen, right? Okay, so right. So we are going to find that, okay, if we were to write our programs here, right, and over here, if we want to maintain or keep the information or hold the information here, you'll find that these are VHDL itself, they are going to infer, means that they come up with a latch or flip-flops to hold whatever informations. So if I'm using a if statement without a else, you'll find that a latch or a flip-flop will be infer. Okay, so whether it's latch or flip-flops here, depending on your these if statements here. If you say clock is a level, using the clock, which is a level, means that when clock, okay, if my clock equals to logic 0, so this is a level, that means that clock is at logic 0, then you do something, okay, and you never put a else at the end here, then you straight away end your if already. No else, you straight away end your if already. In this case, you are going to find that because you are using a level clock, a latch will be infer. But if I am using something like a statement like this, if clock, remember the clock event, any bit clock equals to a logic 0, then I do something, okay, something, and I never put a else, okay, I just say and if no else, then you find that the system or the VHDL, okay, program in this case here will infer a flip-flop for you because you are using the H. This is a H event. So this one is a logic 0 event, okay, a H detect. So they infer a flip-flop. This one is a level. We are talking about this part, level. So they infer you a latch here to hold your information. So here they tell you simulator needs to hold previous output under certain condition if no else statement is included. You never put, they pandai, very smart. They come up something to keep your list information. So if you don't want this something, okay, to hold your information here, of course, okay, before you end, okay, insert a else statement, okay, insert a else statement, else something, then you find that, you save, okay, the simulator for holding your previous output. Okay, now look at this example here. Process. We only focus on this architecture. In my list process here depends on cell selector and A input. Begin. If my cell is a 1 level, then my Y will be assigned as A. So there's no else. So where I end if already. Okay, so you find that if this is the case here, the system will infer you a latch. So to avoid unwanted latches, include an else conditions. So the whole this part here. Here is trying to tell you to write a better programs. Okay, now another example. So under the case statement, okay, we can use when others now. This now here means it's no operation. No operation. No operation. Okay, so you can do this. Okay, say case statement using this one can infer lectures if type is standard logic or standard logic vector. So look at this example here. Now I have a begin case cell is, okay, you see my cell here is actually okay declared as a 2-bit, but over here I only have 2 combinations. 2-bit by right should have 4. All right, but that is the minimum. On top of the 4 here, you may have conditions like don't care condition, high impedance conditions, and so on. So over here, all these are not considered. So I only interested in when my cell is 0, 0, I assign my Y to take the input A. Other than this, okay, when cell is 1, 0, I assign my Y to take the input B. Any other than this, no operation. Okay, if no operations here, then these systems here will need to hold this condition, or when this come no operation, when this come no operation, things like that. So if this is the case here, okay, they will infer the lectures for you, okay. So use a lot of these unwanted lectures. So prevent this from happening, what you can do is you can put when others, okay, you assign Y is the output, right? What you want the Y to be, okay, let's say a logic 1 or a logic 0. So with that, okay, understood that anything not these two all jump into this part. So with that, okay, they don't need to hold extra lectures. Okay, so this one especially useful, okay, when you are writing a big programs whereby your hardware is insufficient already. Okay, so you don't want simply wasted whatever lectures, whatever flip-flops in the hardware. All right. Next, okay, how we can we will infer these flip-flops here. So basically, it's on the edge, okay, edge detecting and edge, okay, event cases, okay, these are event, okay. So use processes and if statement to describe sequential logic. All right, if statement detects a clock edge. So you can write VHDL using this word rising edge or this one. They mean the same thing. Or you can use the word here falling edge and this one indicating falling edge. This one indicating this falling edge. This one rising edge. Okay, okay, falling edge, rising edge. This one. All right, so you can Either write this way or this way. They means the same thing. Okay, so look at this example here. Architecture behave of DF is, DF stand for my these are D flip-flops here. I begin. Remember, this is just a name for this process. With or without is okay. All right. So process clock. When there's a clock change, I am going to begin all this. So my clock change at time, I must detect whether is it rising edge or falling edge. So in this case here, because clock end at this one, so rising edge, when if rising edge, then your Q you assign to take the D input. So then you end if. Do you have a else here? Else what am I going to do? Else what am I going to do? Else actually your Q here remain no change, right? Okay, remain no change. If Q is a wire, you can do it this way. If Q is a wire. But if Q is not a wire, sorry, this is wrong because your output cannot appear on the right hand side. I repeat, your output, if Q is declared as output, this is wrong. All right, because Q cannot appear on the right hand side. Output can only appear at the left hand side. Okay, so this is an example to tell you that, okay, you can prevent using or inferring, okay, ledgers if you don't want, okay, things to happen at their, if you already know that, okay, this is something that is going to happen, okay, Q is going to take the input D. If this is not the condition, your Q remain unchanged. So you can just write extra one statement to say that, okay, my Q is unchanged. Okay, so depending on whether you declare your Q in this case here as a wire or not, but logically it is this way. Okay, so look at this example here. This is again is a D flip-flop, but additional control now reset. We have an additional control of reset, and this reset is active low. Okay, active low reset. And you're going to find that this reset here is of higher priority as compared to my clock. So we call this reset here as asynchronous. Okay, asynchronous, not synchronous. Like asynchronous means it's not synchronous. Not synchronous with what? With your clock. So they are of higher priority as compared to clock. So look at this part here. My architecture flow of DF clear is begin. This process depends on clock, depends on reset. When clock change, I need to run one time. Reset change, we also run one time. Okay, so I begin. If my reset is a 0, remember I told you just now, active low reset. If my reset is a 0, then my Q is always 0. That means not working. My Q always give me a 0 only. Not working, although my clock is changing, although my D is changing. Okay? Not working, not functioning. You clear the output to 0. Okay, if now reset is a 1, then automatically they will jump into this statement here to check whether my clock is it a rising edge. If yes, then I take my Q here, okay, assign my Q here with the D input. Okay, I end if straight away. I never have a else. Okay, where is the else? So logically, actually, it's correct. No problems. No problem. It's just that the system itself, okay, infer a latch for you only. Use extra hardware. That is the latch. Okay, so you go and send this program for compilation. No error. No problems. Maybe they give you a warning. No? All right, remember the warning? So I ask you, forget about the warning, okay? Logically, it's correct. So system infer a latch for you in this case. So I end my if without an else, infer a latch, then I end my process and my these flip-flops here. Okay, and this is a asynchronous low reset or active low reset. Okay, next, another example. Now this part here is dealing with synchronous. Okay, reset is still low, and they have also an extra pin called enable. I sometimes don't want this flip-flop to work. It's not reset, I just don't want it to work. Then I can put in this case here, put a 0. Well, okay, put a 0 to it. Then that means that my this flip-flop is not functioning. Okay, in some cases in the design you may need to do so lah. All right, so if I want it to work, okay, I change these pins here to 1. So you see there's no bubble here. No bubble here means enable is function with a logic 1. This chip or this IC here, this entity here, only going to work with if my enable is a 1. Same thing. This one here, reset you see a bubble. If you connect a 0 to it, this one here will become a 0. But will it become a 0 immediately or not, depending whether you are talking about synchronous or asynchronous. So this one here is a synchronous. So synchronous means that they are controlled by clock. Okay, only clock change, then only they will check this reset, they will check enable. So clock is the highest priority in this device. Whereas the previous one is asynchronous, reset is the highest priority. So you see in the program, I check reset first. Okay, so asynchronous. Come to this example 2 here. I begin, the first thing that I check is the clock. I must make sure that my clock is of rising edge. Then only I will do all this. If this is not rising edge, you can skip. Straight away go to the end if. Then you end your process. So with this, we say that clock is of higher priority, the highest as compared to your this S reset and your enable. So we say that this is a synchronous. Everything controlled by the clock. Okay, this D flip-flop is a synchronous low reset, active high enable. All right, synchronous tells me that everything controlled by the clock. So let's look at these programs here. If my clock event and clock equals logic 1, means rising edge, then only I do this. So because I check this one here, only this one change, I need to do all this. Then now you look at the process. My process here depends on clock only. Okay, some children may ask me, can I put here, put clock? Can I put here RST and also EN? Answer is, if you send for compilation, no error. But your programs will be slower in the sense that, okay, if my S reset changing, they also will run this process. But when they try to run this process that time, the first thing that they check is still the clock. Clock, not rising edge, not going to do all this already. You waste your time, right? So although reset changing, you also come to here to do the checking of the clock already. Okay, you are wasting time. Same thing. If EN enable here change, first thing I check still, am I at the rising edge? Answer no. And if. No need to do all this already. So therefore, the process here, okay, whatever your input, okay, input port, okay, in this process here, we must really, okay, think about it thoroughly. Make sure, okay, we don't put in unnecessary, okay, unnecessary input such that, okay, slow down the whole process. Okay, so first thing I must make sure I got rising edge. Then second thing I check, okay, is the reset equals to 0? If yes, I do this. If no, I come to here. If no, so straight away come to here. Okay, check whether my enable is it a 1. Yes, then Q will be assigned with the D input. If enable is a 0, straight away from here you can end if already. Every if you need to end. So therefore you arrange it, okay? Same, okay? So that we know that this if is for this one. This end if is for this one. So in line. In exam, okay, when you are writing program, if you didn't have a correct formatting, I straight away, okay, minus 2 marks or 3 marks depending on the programs. So this is the basic of writing program. You match it, okay, in line, and end your process because this begin is to begin the process. Okay, so I end my process, so in line. So end my architecture. So in this case here, I also don't have a else. So logically, no mistake. Compilation successful. Okay, maybe you get some warning. All right, because they infer flip-flops in the system or in the simulator itself. Okay, another example. So process based on clock only. Begin checking my clock. Is it a falling edge? Then check my enable. Now this enable is active low. If enable is at logic 0, then my Q, okay, will be assigned to take the D. Again, where is the else? All right, no else. So this end if is for this one, this is for this one, this end process, because I think I do that time, okay, I forget to pull it down. So this end process is for this begin, I end my architecture. So by right, okay, now should be able to understand most of them. So ask you a few questions. In this model, positive edge or negative edge triggering flip-flop? Are we using a negative edge or positive edge flip-flop? Which is the one? Can anyone answer? You can type. I can see here. What do you think? Positive or negative edge? Answer is going down. Negative. Thank you. Correct. Negative edge. Okay, negative edge. It's not a 0 because it's not a level. It's a edge trigger. Okay, edge trigger. Okay, next. Is the enable synchronous or asynchronous? Synchronous or asynchronous? Anyone? Are you all with me? A is asynchronous. What makes you think that this is asynchronous? Now, compare here. Synchronous. I check clock first. Asynchronous. I check whatever pin or whatever input. Okay, so this is a asynchronous reset. Now back to these questions. What are the conditions that I'm checking first? Clock right. Clock right. Clock is the one who control the whole thing, right? So in this case here, my this enable, is it higher priority than clock? Answer no, right? This enable is still controlled by the clock. Okay, therefore, answer should be asynchronous. I check clock first, then only I check enable. So it's a asynchronous. Sorry, it's a synchronous enable. It's synchronized by the clock. Clear to all? Okay, last one is very easy. This enable here, active high or active low. Yeah, active low, because you check if it's low, then only it work according to the D flip-flop. So answer is low. Okay, answer is low. All right, so that's why when you write programs at time, you must know what are the entity, what is the features of the entity that you want. So you try to implement it using all these codes here. Okay, next example 4. Now over here we are talking about 4-bit register. Okay, this 4-bit register is formed by 4D flip-flop. Okay, so this is a complete programs already. Entity DF4 is one input only. This one input here is actually in terms of a bus. Okay, so it's a vector 3 down to 0. One common clock. One output, but it's vector. So actually 4 output lah. All right, 4 output. So, and my this entity here. Now, begin process. You'll find that, okay, we don't have a sensitivity this. This is because we use the statement wait. I am not going to do anything. I just sit here and wait. Wait for what? Wait for a rising edge. Wait for a rising edge. Then my Q output will be assigned taking the D. Make sure that, okay, their length is the same. This is 4-bit. This is also must be 4-bit. Then straight away, the D0 go to Q0, D2 go to Q2, D1 go to Q1, things like that. They are very pandai one, okay? They match accordingly. All right, so you end your process. So in this case here, I don't use if statement. So I just directly this one here. So is this better compared to use the if statement? You all can test out. You are going to find that their output here is a little bit slow because wait time is slower. All right. So when you are using this wait statement, there's no input in this sensitivity list. All right. And of course, okay, when we draw this, actually there are 4 of them. Remember when we use the block diagram that time, the 3 ... 0, 4-bit. This one here also 4-bit. In the block diagram, of course, we can put it this way, but in actual VHDL is labeled as in this form. Okay, so next. This example here, don't know why the color is so ugly. Okay, this example here, I'm trying to come up with a counter. Counter means that they are going to do counting. Their count, okay, will increase by 1 if it is up counter, or decrease by 1 if you are referring to down counter. So in this example here, we are talking about up counter. Up counter means count up, so we call it as a up counter. So when we write program that time, okay, of course, you may find that this is the program that we wrote. So to look at this one first, okay, we look at this first. So if I'm writing a program for this counter, up counter, I must know how many bit I want it to count for. What is the maximum count, okay, that I'm designing here. So in this example here, we are talking about 8-bit. Okay, so this counter, they can be clear all at one shot. And I can stop the counting. That means that make it stop there. Okay, if you count until say like 13 already, okay, stop at count 13. So you have a count enable. Okay, count enable to make the counting stop. This one here is to clear the counting. Oh, clear means that clear it to 0. Start the count from 0. This is stop the count. This is the clock input. Continue with the counting. You need a clock signal to synchronize the counting process. And my output here, 8 bits. Okay, 8 bits. So over here, I need to know what is the current count. Because now count 7, for example, the next count must be 8, right? So I need to know the current count. What is the count number now? So in this case here, I may need to feedback this output to the input for processing. Therefore, instead of using in out for this output here, well, it will be better for us to use signal. This signal here actually is trying to feedback the output to the input. And you are going to find that this signal here will be directly connected to this Q output and make it go to whichever entity that require this information. Okay, and the length must be the same. Okay, 8 bit. Okay, so now here the process here depends on clock, depends on clear. I put my clear here. So my one question here, my this clear here is a synchronous or asynchronous? This clear here is a synchronous or asynchronous? Anyone? Synchronous or asynchronous? For this CLR clear here. Class, are you still with me? Asynchronous, yes. Okay, ASYNCHRONOUS. Okay, this is asynchronous. So because this is asynchronous, you find that begin the time I check clear first. Clear is of higher priority as compared to the clock. Okay, if my clear is a 0, then my wire signal is of this condition. While 80, I still can manage, okay, type in the 80. But is there any other better way to do it? Can I put it as, so I replace this whole thing with others, or these others here, I am going to assign with all 0. So that to say that you have 80, you can put in this. You have a 32 also, same thing. This same statement go in. They will fill up all the 32 bits with this 0. Save a lot of time when the length is very long. So learn up this one. All right. So I make my count here become 0. Clear it to become 0. Okay, if my clear is a 1, I jump to this else if here, check my clock. Is it at rising edge? If yes, then I check my this count enable. Your this count enable is synchronous. This is synchronous. Why? Because it is controlled by clock. Clock first, then only this one. So this is synchronous. Okay. So I check my clock count enable here. If it's 0 active low, then I increment. Add 1 to it. And this one here unsigned. Okay. This 8 bit here also unsigned. Okay. MSB bit, okay, represent a number instead of a sign bit. All right. So I increase, okay, count increase by 1. I add my this if and my this if. So this is for here. This one is this one. I add my process. Now only I transfer whatever is my CNT here into my output. A lot of students forgot about this. Okay, so no output. Go eventually finish everything already from the wire, okay, I assign the conditions to the Q and I end this architecture. So this is a program that we write. But for the case of a simulator, how do they do it? So you may find that, okay, they may come up with something like a block like this. Okay, let's understand this one here first. I'm using D flip-flops. Okay, because anything to do with counter and so on, you definitely need to use a flip-flops already because they have to remember the conditions. All right, so the easiest one, D flip-flop. This D flip-flops here, clock input, got a clear, which is a active low. Okay, active low clear. And these D flip-flops here, 8 of them. Okay, inside here got 8 of them. This is a bus, 8 bits. So inside here got 8 D flip-flops. All right, next. Because there is a selection of count enable. So it is like function like a multiplexer. Decide. Should I count increase? Should I, okay, don't count the increments, things like that. So count enable will manipulate all this. Okay, it's an active low. Active low. Okay, so actually there are also 8 of 2-to-1 multiplexer inside here. Okay, 8 of them, 2-to-1 multiplexer. Next, I got an incrementer. This incrementer here will cause, okay, count to increase by 1. All right. Okay, so in order to know, okay, what is my output here, I must know, currently what is the count now. All right, so if count here 7, I add a 1, here become 8. If count here is 13, I add this one here become 14, things like that. Okay, in integer. So, okay, these 3 components here, now they are linked, they link it in this way. Of course, okay, Q, my output here, 8 bit. Now, I need to know what is the counting at this case here. So, because this Q is the output, so I use a wire. Okay, make it connect. This is a wire, CNT is a wire. Make it go to the input of my multiplexer. Make it go to the input of my incrementer. Okay, let's start off this one here. If my clear is a 0, okay, clear is my 0. You are going to find that this is a 0. My clock keep on running, no problems. So clock is always running. So if this is 0, go in. Okay, sorry, okay, I shouldn't put a part here. Okay, so this is my integer 0. When this 0 go in, they come to here 0. Come to here also 0. This is the starting when my clear is a 0. If my clear never change forever 0, now this is the result that I'm going to see. My Q is always 0 value. Not working, this counter. Okay, to make it start working, I must make sure that my clear now change to 1. Okay, my clear now change to 1. Okay, just now it's a 0. 0 come to here, 0 come to here. So with this 0 come to here, my incrementer automatically will increase 1 plus 1. So from 1, this is 0, increment to 1, it tends to become integer 1. This 1 is at this input, this 0 is at this input. So do I want the count or not? Answer if it's yes. Okay. Answer if it is yes. This is the active low. So if it's yes, this one here will be connected to 0. When 0 go in, look at this program. Count. If the count enable is a 0, then they will choose this one as the output. So this is a 0. Inside here, this 0, okay, and with this, okay, this 0, with this 0 here will cause this one to become a 1. This is a 0. So if this is a 0 go in, they will choose this one as the output. So when come to here, clock comes. 1 will be appearing here. And with this one, back to here. So you find that this one here now change to 1. I put at the bottom, here change to 1. First clock pulse successfully increased my counter from 0 to 1. Then next, automatically this one will add another 1 to it. So you find a 2 appear here. My count enable, yes, it's still a 0. So 2 will appear here. Next rising edge comes. This 2 will becomes the output. And this is 2. 2 will be fed back through this wire. Here you see a 2. Here you also see a 2. Then this 2 plus 1 give you 3. So this is always higher than this one count. Then depends on my count enable. If it's still a 0, 3 will appear as the output. Rising edge come, 3 will appear here. Okay, continue. This one will appear here. This one will appear here. Same wire, okay, appear here and here. Let's say now, here, I change from 0 to 1. The count enable, I make it become 1. Then you are going to find that this 3 will appear here. They will select this one as the output. So 3 will appear here. Rising edge come, this one will appear as 3. The count never increase because you disable the count here already. You disable this one. So next clock pulse comes, I still see this figure. No matter how many clock pulses come, you still see the same figure, never change, because you disable the counting already. So if you want to continue the counting, change back this one to 0. Then you find that the count will start continue from after 3 for many, many times, they change to become 4. Okay, if this one here output you a 4, and with this 0, they select this 4 as their input to the D flip-flop. Then the count will continue. Okay, so we are writing the programs in this case, but the VHDL itself, okay, inside the hardware that you all are going to see in week 5, they will make use of whatever components they will generate, okay, multiplexer for you. They will generate the incrementer or the counter for you. Use whatever flip-flop available to form the programs that you are written over here. So it's easy to write program than go and build the hardware, isn't it? Okay, so you write this program, system build this one for you by itself. This is the whole thing, and it's for you to go and understand these programs here. Okay. So over here, look at the note. The output Q must be copied to an internal signal or wire CNT, since an output port cannot appear on the right-hand side of the assignment operator. Remember I said this just now? I said this is not allowed, okay, if this is the output. But if it's a count, you can have a count CNT. Okay, this is a wire assigned as a CNT plus 1 integer. All right, this is okay because this is a signal. Same thing over here. Maybe I put it down this way instead of just direct like that. So I put it as a plus 1. This very similar concept. You find that this one no. Why? Because this is cannot at right hand side. Okay, output cannot appear at the right hand side, but signal can. This is the reason why, okay, we introduce additional signal in this case. All right, to make the to meet the syntax of VHDL. Okay, so 5 minutes. Oh, can finish this one, Okay, this is we are talking about now, okay, trying to understand shift register. We are doing shifting. We want data, let's say you got 8-bit, okay, sorry, put 4-bit easier. Let's say I have a 0011 starting that time. I want it to either shift left or shift right. Suka hati. Now, in this example here is the right shifting. Okay, right shifting. So you are going to find that signal like moving this way, right shifting. So what we are going to do is we write a program so that signal moving. This one come to here. This one come to here. This one come to here. This one here going to fill in with a new data. New data. In this example here is our D in, data in, D in. All right. So this is after one clock pulse, you got this. After another clock pulse, you find that, okay, this one, this is D in 0. Okay. So this D in 0 later on will be inside here. This D in 0 can be a 0 or 1, then become D in 1. New data comes in, and this one will be shifted here. This one will be shifted here. This one seems like missing in this case here. So it depends on your program, okay, where you want this output to go. You write. But in this example here, it's trying to show you how you can do shifting in VHDL. Okay, so this is the concept. Okay, we look at these programs here. This programs here got a clock as input, D in as another input. Okay, output 8-bit. 8-bit. All right. So over here, we also use a signal because you find that, okay, you cannot have this Z here appear at the output on the right hand side here, okay, this output cannot appear on the right hand side. So we make use of a signal to help us to solve this problem. So my signal A, same length as this one. Actually, is similar to the Z here. All right. So I begin process clock. So you find that begin if rising age. Then I take my A equals to A6 down to 0. Remember, you have this one here is 8-bit, but here you only consider 7. You concatenate with a D in. Okay, so you find that, okay, original A, I only take this. I only take this one. I leave out the MSB. Okay, I only take out the main. Okay, so this one here, they go start from the second MSB bit. Okay, second MSB bit. So if this is 7, you take 6 down to 0, then you anyway concatenate with your D in and put it into the new A. So imagine this is original A, this is the new A. This A is this one. Okay, you start from one bit, okay, after the MSB. You concatenate it with D in and you move to this new A, which in this case here, this new A is this one. Same thing, shift. Second clock pulse comes, location interchange. This one, you are going to put it here. Whatever is the new data, you put it here. Then, okay, replace the old one. Then to get the new more data, you do the same thing as well. So your data in, you can keep on changing. So they will just concatenate with the whatever new data over here and shift in, like what I explained over here. Okay, so eventually after a few clock pulses here, the old data all will gone. Okay, so this one will shift here to D in 0. This is a D in 1. Later on is the D in 2. This go in. So How this one can come in is because you concatenate, okay, and copy whatever here into the new A. So all these are A, okay? So you can call that this is A0, this is A1, this is A2, this is A3. So every time the A1, okay, information come from the A0. Then your A2 later on, okay, come from the A1, whatever. Okay? They just replace it. So with this, okay, you are seeing that like the data is moving, okay, to the right, okay? Okay, moving this way. So of course you can move it the balik way also can. So in that case, okay, you can have a D in concatenate with say A with the depending, okay, you want it is 7 down to, okay, 7 down to 1. You replace, okay, the MSB. Okay, replace the MSB. So you take the A, okay, assign with this new A. Also can, it's a different way of shifting. Okay, so this part here is always your, these are MSB. They will go by sequence. So A7 up to the A0. Okay, in terms of location, A7 up to the A0. Okay, well, they are moving this way. Yeah, I make a mistake. It's moving left. Okay, this is moving right. Okay, why they call it right shifting? Okay, so this is how we write our program. Data is from right, okay, but seeing this one here is moving to the left, okay. But anyway, okay, you do the time, you must clear, okay, what type of arrangement that you want. Okay, so just nice. My planning is today end here. Okay, we are going to stop here for today, and I'm going to see you again on Thursday, right?